Hello all, welcome to my channel. Uh, this is a new video in the series that we are doing on the 5S of Spark. In this video, we will discuss Skew. So let's get started. So whenever we process data using Spark, Spark loads the data in memory and logically divides it into partitions. Data skew happens when we have certain partitions which has significantly more data compared to the other partitions that we have for that data set. What all could be the reasons for that data skew is like joins, grouping, imbalanced data distribution. So let's understand why join causes an issue. Join causes an skew in Spark data frame. So join, when we do say that join two tables based on certain key conditions, conditions that we mentioned that okay, column 1 is equal to column 2, let's say. So all the keys from both the data sets which are same lands up into the same executor. That's how Spark does a join. In most cases, I'm not talking about broadcast where the whole table itself is broadcasted to every partitions. That's a different case. But in general, apart from broadcast joins, this will happen that the keys with the same uh, rows with same keys from both the tables will land up in the same executor. But the challenge here is that if the data is distributed in such a fast way that the keys that on which we are joining have more data compared to the other keys, or the key distribution is different, then we will end up with certain rows or certain partitions having very large amount of data, and that will cause an skew. So ideally, we believe that we should be seeing a distribution like this on the right side where I am hoping. So it's an equal distribution, kind of like at most three, at least one kind of distribution is there. But in the right side, left side, if you see the many data is going to partition one and only few is going to partition two and partition three. So this join that we do can cause an imbalance, and this causes an skew. Then we have grouping and aggregation. Same rule applies in here. When we say group by, so when we are doing a group by on certain column, all the keys, all the rows which have a certain key, or the grouping key, or for in case of aggregation, the aggregation key should land up or must land up in the same partition so that it can be aggregated. Some aggregations do allow partial aggregations, that is a different case, but which does not allow partial aggregates will end up on the same executor. And if the distribution of that data is high, then again there will be a chance of uneven partitions or uneven uh, partitions coming, or uneven size of data being processed by different executors. That again causes an skew data processing. One example can be, for example, let's say if we have a data set where everything is divided uniformly, but we have, let's say, a lot of nulls which don't have a category. But while doing a group by, nulls will fall into the same, like all records having null in the grouping key will fall into the same executor. But if we have a lot of nulls, that will again cause an skew uh, is problem. Then we have imbalanced data distribution. So this is something which is inherent. This we can't control in a sense that there are data sets which are by default or by its nature itself they are skewed. For example, let's say if we take example of let's take an example of IPL and fan following that happens. So when the matches are happening between, let's say, MI and CSK, which two have very large following, large follower base, or let's say MI and RCB, they also have a large follower base. So at that time, the events happening will have, or the click stream generated will be very high compared to, let's say, a match between let's say Delhi Capitals and Lucknow Super Giants, that they don't have that much of fan following. Other example can be that uh, for example, let's say if we try to identify traffic pattern in India, so we will have a few zip codes, let's say Bangalore, some areas of Hyderabad, some area of Delhi will have higher number of traffic compared to other state, other locations. So if we try to process that data in one go, that those partitions might have imbalanced. By inherently it is imbalanced. So we are uh, so the data itself is in such a way that it is imbalanced and it will cause an skew. Okay, so let we understood what is an skew in Spark. Now let's understand what happens if there is an skew. What is the challenge that can happen? So as we said, that Spark is processing all the data in parallel, and let's say it has, let's say, 100 tasks. So we have 100 partitions, so 100 tasks got created. All other tasks had, let's say, 100 records to be processed, and one partition is there which requires, it has 1,000 records. So all the 100 records, executors which are processing that 100 records will finish fast. They will just finish, and then they will keep on waiting for the task which is the bigger one, which has, let's say, 1,000 records. And let's say if we assume a linear scale, so if it takes 100, let's say it takes 1 second to process 100 records, then it will take 10 seconds to process that uh, 1,000 records, right? So what will happen? So initially all the executors will start at the same time. The smaller ones will finish first. The large, which one has a large skew, will finish last. But the time when it is running, other executors can't do anything because they have to wait. That whole stage needs to be completed so that it can move to the next stage, right? So the executors in that case, although they don't have any work, will sit on idle, and whole process will slow down. So the stage which ideally should complete in lesser time will take a lot more time to complete, and it will create a wastage of resource. If we had event distribution, things would have worked parallelly and it would have completed faster. Then other challenges, let's say if that same scenario that we have, that we are processing 100 records, and let's say we are doing some transformation on those records which requires memory. Let's say we have to hold something into the memory for each row. So storing something for each row in memory for 100 records will, let's say, take X amount of memory. But if we extrapolate it in the linear sense, again we will have the same scenario where we will be needing 10x more memory in the other executors. And if that executor which is processing the larger skewed partition, if that doesn't have that memory, it can cause the disk, it can cause spilling to disk, it can cause a lot of GC overhead because objects are getting created and deleted, or it can even result in out of memory exceptions as well. So this is another challenge which comes with Skew. Now, how do we find that our job is having skew issue, or our job is having an skew problem? The simple way to find out is we can go to the history server or the Spark web UI. The history servers are persistent, so they can be queried after the job is finished, but the live web UI, which runs on 4040 port, will only be available till the job is running. So we can open the history server UI and we will see something like this. See, this is the timeline. This is the event timeline. So there is a tab in history web UI or history server, that where you can see the timeline. So this timeline says there were many jobs. So for example, uh, like this. So one job started at this time, not a job. This is a execute event timeline, that okay, some executor started to process the task and it kept on processing for very long. The others got finished fast. The reason for this is that this data, this task is running something which is having an skew problem. Now, if we go and see there is a tab for task summary. In that page, if we go, we will see like this. It will say uh, for all other things, we will see something like this, which says there is a how many records where let's say although it says for shuffle, but it can be extrapolated to the, because shuffle will only happen, right, because we have a lot more data to process. So see, the median for this stage, uh, the tasks that were getting processed were processing, let's say, 3.9 kb of records on a median, and the 75th percentile was taking 25 kb. But see, the max one is suddenly 116 MB, which is way higher than the other ones. In the number of records, if you say 517 versus 3548 versus it is almost 17 million records, right? So this is a clear indication that there is an skew problem going on in the in the job. So how do we solve these issues? So this is a summary table. So we can, what we are going to, what are the approaches that we can take to solve the issues that we have with skew. So it depends on what is the source of this queue. For example, unknown or anomaly data, let's say as null, blank, string, or unknown values which are there. So one approach is to filter them or handle them separately. So that is for the those kind of scenario. In joins, for example, let's say all the cases we are talking about is for equijoins. So let's say we have an equijoin, and so one approach is broadcast if possible, because that does not require keys to be present, like that it does not repartition, so it will work fine. Then comes, let's say, if we are joining and if we it is possible for us to provide hints, so we can provide skew hints while doing the join, or we can leverage AQE. So AQE has a concept of dynamically repartitioning the data based on the runtime stats to improve the processing. So if we have a very large partition, AQ will try to divide it into smaller partition, then do the join, and hence it will process, it will not cause any skew. Or there is another approach where smaller tasks gets coalesced as well. So AQE does help in join, helping skewed joins. Then we have skew coming because of aggregates. So what we can do in there is we can leverage partial aggregate. So partial aggregate happens for all the native aggregate functions which are there in Spark. Those functions do support partial aggregate. So what will happen? Each partition will do a local aggregation and then send it to be combined together. So that is something we can leverage. And if we are writing our own aggregate functions, then we should try to implement partial aggregation there. If that is not possible, then we can do a two-stage aggregate with salting. Two-stage means that we uh, divide the data set in two sets. One where one with skew, another one without skew, and then we do a processing of both individually. The skewed ones we will add salting to it, and then combine the results from those aggregates to the ones which are fine. But here there is one case that we should be handling in here is that are those aggregates additive or semi-additives or non-additive at all? So let's say, for example, sum can be calculated in two stages, will not cause an issue. But let's say we are trying to calculate average based on certain category. So we'll have to take care of the counts as well. So we can't simply emit sum. We have to emit sum and then the count, how many elements were or how many rows were used to arrive at their particular count. And when we are joining, then we have to handle that case, right? That if we had sum with coming from, let's say, x numbers, and there was another partial sum coming with sum plus y numbers, then the total sum becomes sum x plus y, sorry, sum 1 plus sum 2, and the average, if we have to calculate, we have to say sum 1 plus sum 2 divided by x plus y, both count, then only we will get average. So that we will have to handle. Other approach is to do a hierarchical or incremental aggregation. rather than doing a one shot aggregation. That again is something which only will be supported for aggregations which are additive. For example, count, sum, those can be done in hierarchical way. One uh, thing to mention about sorting. So there are two approaches to sorting. One is where we find the key which is causing the skew. We create a different data frame. In that data frame, we apply the sorting mechanism in there, and then we process that. Then, and we have one other data frame which is only having non-skewed records or keys, and then we process them separately, and then we join it. We do a union of all those things, and then we give back the results. And the other one is where we do a uniform salting in the overall data itself. Like the whole data frame is salted, and then uh, on that we do a one shot aggregation or one shot join, whatever we are trying to do. So the challenge with the uniform salting is that the salt factor uh, or the skew factor that we have will define how good that salting will work. For example, let's say if we have a very skewed, like let's say that the average size of the partition is, let's say, 300, and one partition is having, let's say, 3000, so approximately 10 times bigger partition is there. But to make that particular bigger uh, chunk or bigger partition into smaller partitions or smaller groups, if we add salting, considering that we have to salt on 3000 rows, and if that same thing gets applied to the smaller ones, we will get even smaller tasks. So that caveat is there, that when we do uniform salting, there is a challenge that the partitions which were earlier small or balanced might get split into even smaller, and then we will have a task overhead. To handle that, we can devise an algorithm, logarithmic approach, rather than doing a plain random. For example, how do we add a salt to a column is something like this. Let's say we have this is a skewed key that we have. So what we do is we randomly select, like we want to, first of all, why we are doing 10, we want to create 10 subdivisions of this larger partition. So if we wanted 20, we could have said 20. So this, what it will get, it will give a random number between 1 to 10. And so the random function gives random fractional values. It will just multiply it by 10, and then this will become our salt, and then we are joining this. So what will happen is, now our key, instead, let's say we had this, let's take the example of the Bangalore traffic that we were saying. So let's say in certain areas, let's say in ORR, Outer Ring Road, we have more traffic. So we want to split the ORR traffic, let's say, in 10 segments. So ORR underscore 1, ORR underscore 2, ORR underscore 3, that becomes this key. But if this is applied uniformly to other places, right? Same way, let's say near HAL air, uh, or Indanagar side, where we don't have that much of traffic. If we apply this just 10 factor there as well, what will happen? It will try to create Indanagar underscore 1, Indanagar underscore 2, right? So that will again make even smaller uh, partitions. So to avoid that, take we can create a strategy where we first, based on the keys that we have, the skewed keys that we have, we apply the salting based on the count of that, and then take a count log of that, and then apply. So in that way, what will happen? So 3000 will get split up in, let's say, 10 rows, 10 buckets, but the 300 ones will only get split by one, or let's say at max by two. So that way we can handle this is salting approach, but that will require certain extra overhead. So if salting is very sorry, your your keys are very much skewed, then it's better to do this isolation and then processing. If it is fairly, let's say somehow it's let's say in the range of 2 to 3 times, then uniform salting can be worked out. The other approach is we can create one more other column, derived column, and we add that derived column to the join condition itself to handle certain join. So that approach is also there, where we can add an derived column to work with skew. And there are other approaches like AQE we have already discussed. In-memory repartitioning is something we can do, but this will only work out in cases where we don't need rows to be ordered in certain fashion. For example, let's say if we have a larger data set and we do a repartition on a number. So let's say we try to fix that we want to have 200 partitions, so irrespective of what was the key on which the join is happening. Still, that will distribute the data, but it is something which might not be the foolproof solution. Uh, Custom partitioning is a better approach, where you understand your data set, you understand the distribution of your uh, data on the keys on which you are joining. So you can write a custom partitioning algorithm and then repartition based on that. So that will create the distribution that you expect your data to have. The other approach is to create buckets in tables, in data sources, which is where it is supported. So with bucketing, it does improve few of the scenarios where we will not see skew that much, because it tries to put rows, it tries to create uniform distribution of files, but at the, let's say, at the top hierarchy level itself, there is a imbalance that it will not help that much. But yes, bucketing is also one option that we can take to solve the problems with skew. So this was it. uh, this video was all about skew. We will have one more video in this series left. We will do that, and then we will move to other concepts. If you like it, give a thumbs up. Thanks.